Great to see you all. I know you're there lurking, but I want you to look up. Keep looking up. Watch the skies. I remember a great science fiction movie called Them, uh, with James Arness playing a monster piece of broccoli. But the warning was, keep watching the skies. A couple of terms. Comets are just giant chunks of ice with a tail, and they come periodically. And they're very obvious because they won't move from one night to the other. This is a comet, of course, you see the long trail. This, by the way, is air glow. It's what you see of the Earth if you're up at the space station. And this is nitrogen and oxygen being ionized, and so it glows. It's almost like the Earth has its own aurora. Asteroids are giant chunks of rock that actually have their own circulation in various parts just by Jupiter. And asteroids commonly bump into each other and split off giant to small pieces of rocks, which would be called a meteorite or a micrometeorite. And we see these sometimes as fireballs or as bolids where they explode, or just a streak. And that streak is a meteor. Rarely, some of the pieces will fall to Earth. And if they survive that trip, they're known as a meteorite. Now, sometimes you think you're seeing light colors, and those are colors. They may be minerals in the meteorite themselves burning up in the atmosphere. And so we can tell a little bit by that. We have long had mythology about meteorites. Perseus, of course, used Gorgon's head to immobilize everyone. But I want to bring your attention to the fact July and August, we go through the Perseid kind of tail. It's a series of micro meteorites, and we get the Perseid meteor showers. We'll talk about meteor showers later. Everyone asked, has anyone ever been killed? Well, some people have been hit, ricocheting off a house. This is still debated because they couldn't find the body, and there may not have been a body. But I always love this little piece of Peanuts wisdom. No one has ever been killed except a dog was killed in Egypt some time ago, although a dog, well, and that supposedly is a true story. No one has yet been killed by a meteorite. However, they do fall. Sometimes they're valuable. This one happened in 1992 in Poughkeepsie, or Peekskill, sorry, and it hit this Chevy Malibu, and the car sold for $10,000, and the meteorite later, and this is 1992, the meteorite sold for what was it? 75,000. Wow. Just this February, there was a great deal of news about a fireball seen going across Gloucestershire in UK. And believe it or not, there are enough nutty sky watchers who not only watch the clouds, but watch the skies for meteorites. And they have their telescopes trained. We have this same system, but they're trained on potential Russian missiles. And they can instantly track the trajectory, and they can tell where the missile, or in this case, the meteorite, will land. And people immediately got out there, found dozens and dozens of what are called chondrites. This is a broken piece of asteroid, and it's made up of bits and pieces of our early solar system and some of the dust from the first Big Bang. So these are time machines, and they're very, very valuable. And we go back to the Big Bang a little bit. When the first galaxies formed and the first solar systems and the stars began to grow old and supernova. And then we're now in this time when we're in a rather middle-aged solar system with a middle-aged star. It should make everyone feel good. We know what's going to happen in another couple billion years to our sun. It's just going to get old, expand like all of us do, and then shrink and explode and go into supernova. But debris from this very early time, almost 10 billion years ago, makes it into our present day. Now, these are all galaxies. I love this. And these galaxies formed about 13.3 billion years ago. We're just seeing the light from them now. They're probably all gone. But our solar system was created by our star and things orbiting it. And a lot of things would bump into each other, break apart, coalesce into planets. And some of the big planets would pull these other planets apart. So there was still much debris, but early planetesimals, isn't that a lovely term? When all this debris would bounce into each other, it would begin to undergo a radioactive melting, and all these elements would move toward the interior. So they would come into this center and then eventually differentiate. So they have a radioactive iron core and then a mantle and so on, like our Earth does today. And at any time, these can be broken apart and turn into fireballs or meteorites or some other thing that we'll talk about. So here's an early solar system. You see comets here, but you see lots of debris and tremendous amounts of debris out here. And these things will, we used to think there was a missing planet in here, but it really is just debris that never coalesced into a planet. And these show you, there's Sun, Mercury, Venus, Mars, Earth. And just beyond Mars, in between Mars and Jupiter is a giant gas planet that has a tremendous gravity and pulls things apart and keeps these things from coalescing. This is one of the asteroid belts. There's another asteroid belt. And it mostly is these things bumping into each other, breaking pieces apart, and sometimes changing their orbits so that they come this way and, well, they come like that, and they will come by Earth and burn up in our atmosphere. Way out beyond, so here's the initial main asteroid belt between Mars and Jupiter. But if we keep going way beyond Uranus and Neptune, there is another, the Kuiper belt, or the Kuiper belt. This is another asteroid belt. And if we go beyond the Kuiper belt, there is a massive cloud around everything called the Oort cloud, where the comets are. And the comets will have tremendous orbits. And this is why it takes so long for these 70-year orbits like Halley's to come by our planet again. But comets rarely form meteorites. Now, one thing we can be thankful for is that comets and meteorites actually would collide with our early Earth and produce water. This is a rarity in the sense that we have liquid water, and it comes initially from hydrated minerals in asteroid meteorite pieces, and of course the comet. So if you like the ocean, you like to drink, thank our comets and our meteorites. The asteroid belt, probably all these things that didn't form into a planet, and they are continued to be just broken pieces because of gravity from Jupiter. One of the interesting things, and why I got interested in meteorites in the first place, besides their just wonder, is all the minerals that are found in here. We get hydrogen, carbon, and nitrogen in asteroids. And then we get iron and nickel and all these other radioactive things. many people are thinking about mining these. We also are concerned because sometimes these asteroids will bump into each other and take a different orbit and could potentially nail us. And these are the main ones that we're worried about. But this is the current census of the main asteroid belt. And there's Jupiter's orbit, and right in here is about Mars' orbit. Somewhere in there is Earth, probably there. So we do run the risk of being annihilated, possibly. But we love to play with this. Of course, Hollywood loves to play with this. Just quickly, asteroids can be carbonaceous, and they're very dark. And this is very important because the life that we know on our planet is carbon-based. Some are very rusty with iron and magnesium silicates, and those things are important. And some are just metallic types of asteroids. About 66 million years ago, a rather large asteroid impacted near Yucatan, created a tremendous series of tsunamis that went around the world, just one after the other, ignited the atmosphere, burned the forest, and made the skies dark for 2 years or so. And this is felt to have been the demise, caused the demise of dinosaurs, and a few little shifty mammals made it here and there. But there's lots of evidence. This crater was discovered recently. This is now buried under most of the Gulf of Mexico, but we know about the Chichaluba Crater and a layer of iridium that is found in high concentration in certain asteroids. Most people did not know what asteroids were until a group actually in 1803 looked up, saw a fireball, and then could actually watch the pieces fall from the sky. So just our understanding that these are pieces of stars, if you will, falling stars, but we know they're not really stars. They're broken pieces of asteroids. But nonetheless, we love to play with the scenario of deep impact. Asteroids seem to be scarier than meteorites. I don't know why, but these are movies that have start with meteor impact, and that usually brings like the blob. The blob came to Earth in a meteor shower, so on. And we still play with this trope and like to scare ourselves. These these orbits, don't worry, but these orbits are potentially hazardous to us. And there are people who are working on how do we deflect them, how do we encounter them, and so on. And some of these are fairly large. You know, this is 900 kilometers, that's 600 miles wide. So if that came in, that would probably put an end to the dinosaurs and us. Recently, some of you have heard of this Oumuamua. This was the original sighting. They did some interpretation, and it was named Hawaiian for scout. And recently, people have been promoting this as actually a UFO. And the trajectory was very strange because it came right by Earth and then went out again. So you may have heard of it. You'll hear of it again, but I don't think we'll see it for another 40 years or so. Here again, this is the asteroid plot. All these big ones that come around, the dangerous ones are in here, but there's some big dangerous ones outside. This shows you the ones that we do, some big ones out here by Uranus. Here's the Kuiper Belt, and then way out here are the scattered trans-Neptunian objects. And we keep track of everything because our demise is quite dependent and could be dependent on these things. Now, Here's a planetesimal that probably didn't get a good start, but once planetesimals form from all these asteroids impacting each other, and you get a melting and a differentiation where the radioactive materials heat up the inside, and you get a core. This is like a miniature Earth. Our Earth has a core that's molten and moves, it has a mantle, then it has a crust. So this is what we call a differentiated body. And meteorites can occur if you just have an undifferentiated body, and this will release stony kind of meteorites. But if these two crack and crash into each other, you can have iron or metallic meteorites, or a combination, metallic and stony meteorites. Now, it's the metallic ones that everyone thinks about when they think of meteorites, because they look like they had come from space. But they are, ironically, the rarest. So if it comes from the core, like this, it's going to produce an iron meteorite. If it comes right up from the lower mantle, it's going to have iron and crystals in it, sometimes diamonds, and these are the most beautiful. If it comes from this very outer, undifferentiated mass of rock, we get a stony. And the reason it's called chondritic is some little circular pieces are left over, probably from the Big Bang and probably from early planetoid formation. So those things are very interesting. And then if you get something from the absolute mantle, and then you will get a stony meteorite without these little bubbles in them. So again, it can come from the core, from the mantle, or from the crust, or just be broken pieces. There's a lot of classification, but we just go back to the center, molten, differentiated, and this is the classic molten iron nickel meteorite. Sometimes you get a little bit of crystallizing, and those are beautiful. Those are stony iron. And then if you get undifferentiated stony asteroids, you get stony meteorites. And the reason they're not found is they just look like stones. And unless you know what you're looking for, most people just kick them aside and don't pick them up. Many people hunt with metal detectors because that's what they think they're looking for, these. But these are scientifically the most intriguing and seldom found. These chondrules, you can see them under different polarizing microscopes and some other things. They go back to our earliest form of planets. And there was probably a dust ball, everything melted, and these things. Here is a chondrule. They look like little round spheres inside a sandstone accretion. Here's a better view. This is a microscopic view. And these are all remnants of the first planetoids that formed early failures, if you will, of planets. Now, some of these will have calcium aluminum rich blibs called calcium aluminum rich inclusions. And you can use isotopes to date these. And when you get this, you get a date roughly about 4.56 million years, or billion years, sorry, billion years. So this is how we age our planet, because these are the oldest rocks that we encounter. They're also very, very beautiful. And this probably represents an early supernova from our pre-solar system. And this is under a slight polarizing microscope. And you see all the chondrules. And each one of these tells an amazing story of the early, well, the late Big Bang and the early solar systems. Chondrule. What's fascinating too, this one is actually from Australia, which is a good place. This one had how many? I can't see it. It had about 20 some amino acid components in it. And almost 2% of this rock, this meteorite, had organic compounds. Interestingly, uh, these could have seeded the early oceans to form life. One interesting thing about this is molecules, especially organic molecules, come in two different forms. That is what are called mirror images or right-handed and left-handed forms. To give you an illustration, you know dextrose, that's a right-handed sugar. Tastes sweet, has calories. But if we made a left-handed sugar for you, you could eat it, it would taste sweet, but you'd have no calories. That's called levulose or sucralose. That's a left-handed sugar. So meteorites have both of these. And these are the types of amino acids. We only need 20 amino acids to form the enzymes and the proteins for life. And all of these were contained in early meteorites. These are meteors, and this one is from Australia that I just mentioned. So all of these, and some of these are capable of forming nucleic acids. So one theory is it wouldn't take much for meteorites to land on our oceans and actually create what Darwin called the primordial soup, where life could just be seeded by extraterrestrial sources. And as I mentioned, this is where the oceans came from. And this is how we think life actually got started. One of the first crucial things was to make a membrane. And these membranes, that is a cell membrane, would form on their own with various experiments from the stuff that meteorites leave behind. And this is a fatty membrane. And once you get this, all you have to have is something that will replicate and something that will metabolize. And so life may be inevitable and would recreate itself over and over again. This is Dave Diemer. He's up at UC Santa Cruz. He's in line for a Nobel Prize. He actually worked with these early meteorites and made cell membranes or liposomes out of the debris. And then it wouldn't take much for sugar to come in here as starches, and one enzyme could make food for this thing. And then you could also have a way of creating replication material. And we think the first material, genetic material, was RNA, not DNA. And if you remember something about viruses, many of the viruses are simple RNA types. Some meteors are really complicated. They have metals and they have crystals and basaltic minerals that say that the asteroids got big enough that they actually had volcanism on them. And we've seen evidence of this. We've seen craters that may be actually formed from volcanoes on asteroids. This is my favorite type of meteorite. These are called Palacites, and this is nickel iron, and these are olivine crystals. And they come from very near the beginning of the core, the metal core in asteroids. Now, if it's actually from the core, the metallic nickel core, then you're going to see some things. You're going to see a burnt crust. You're going to see flow lines because these metallic nickel iron meteorites melt, and you will see kind of a patina on them, and high nickel and sometimes high iron to the point that it is magnetized. And these are very beautiful. Another thing you'll see is kind of what are called Retimoglyphs. They look like little thumbprints, and this is one found in Saudi. And you also notice this shape. These shapes are very important because they're the most efficient shapes to go through our atmosphere. Also, the outside will fuse into a crust. And sometimes you see these ablation lines where it melted and it streaked back. But this is very important shape because this is what we now model our re-entry vehicles. But many of these metal iron, even small ones, will show a shaping by the upper atmosphere. Another really beautiful aspect of these nickel iron, if you cut them with a very powerful diamond saw, you will find a pattern of nickel, iron, and other alloys streaking it in what is called the Widman-Staton pattern. And these are very, very beautiful. People make knives out of it. I should bring mine in, actually. Sometimes you get these crystals. There's an olivine crystal. And sometimes you get really, really weird shapes. But as I mentioned, the most common that are found are only about 6% of the falls. Finds are what you find on the ground. This is what falls out of the sky. So the most common fall are these chondrites or stones, but they're not often found, but they're much more valuable. Where do they come from? Basically, the asteroid belt, other belts, the Kuiper's belt, sometimes the Oort cloud, sometimes from our own planets, and sometimes from our own companions. We do have moon meteorites and also Martian meteorites. Let's go by the classification because it just gets too out of hand. Some very famous meteorites. This one was found up in kind of central Oregon, just south of Portland. The Indians long knew about it, and it probably washed out of central Washington with a giant flood. And they would come to this and try to get metal off of it, but this would collect fresh water. It was dug up, moved, displayed, and eventually sent to the Smithsonian. This is the Hoba, which is one of the largest known, and in some cases considered the largest known, at least historically. But since then, all kinds of meteorites have fallen and people go out there looking. Admiral Perry, who may or may not have made it to the pole and probably didn't, but he did discover way up on Cape York giant meteorites that the native Inuit, Greenland Eskimo, knew about, would bang off pieces and use for tools. And he underwent a couple of expeditions and stole these and then brought them back to the American Museum of Natural History. Now, interestingly, most of the meteorites are incredibly tiny, but they burn up very brilliantly. And so rare ones like the iron of Willamette and some others, it's rare to get anything really big over 50 pounds. But we do know that some things hit us once in a while. June 1908, nobody quite sure what it was. They heard it, they saw the flash, and when they finally got out there, all the timber around this area was flattened, pointing outward. We can estimate the size of it, but we don't know what it was. It might have been an asteroid, or it might have been a comet or an asteroid, and it exploded above ground, and that's probably why it flattened. There's no evidence of melted iron or silica-rich rock anywhere. Now, one thing to be aware of, recently we went through a couple of beautiful meteor showers. We're headed to the Aquariids in early May, but the ones I want you to be aware of, the Perseids, sometimes called St. John's tears. They happen in late July, early August. And this particular orbit drags a lot of debris with it, and so you will get, actually quite a number, maybe 100 an hour. You have to know where Perseus is. And here's Perseus uh, uh, just below Cassiopeia in late July. Pretty easy to find, just look for the triangle or Pisces, but Perseus looks like a teapot somewhat. Now, Chelyabinsk in February 2013 made worldwide news because it was photographed so much and that it caused a great deal of damage. And it had a very low trajectory. It came in at around 29 miles and then it just slowly came down, photographed the whole way. And then, of course, everyone went out to find pieces of it. It was a big rock and it did break up. And you can now go to various shows or dealers. If you know the name, if it creates a historical fall, then they're much more valuable. And people have long valued them as omens, something to make a wish on. There are lots and lots of beliefs. Sometimes you have to make 3 wishes before the meteor disappears. But some people think they're bad luck. Some people think they really early beliefs is that these were souls passing into the afterlife, or they are the spirits of shaman traveling, say, looking for the reindeer, traveling for looking for evil. They usually portend bad things, although they can also portend good, a turn for the better and for wishes. There's evidence in Native Americans, especially in the mound culture of central Mississippi Valley, but here are Egyptian remnants. These were beads beaten, probably heated and beaten into either beads, ornaments, daggers. King Tut actually had a dagger made out of a meteorite and then, of course, a gold sheath over it. The holy black stone that sits in the corner of the pile there in Mecca, and people move around trying to touch it or kiss it. It was blessed by Muhammad, and it has been there for centuries. Here is the black stone. It is thought to be a metallic meteorite. Now, you may have heard a little bit of people attempting to mine meteorites because of all the rare earth, rubium, platinum groups, rhodium, which are all used in radios or cell phones. And they're very, very common in asteroids. So the guy, Melon, whatever his name is strategies. Here's an asteroid that obviously shows impacts, so that this one, what is called Psyche 16, is worth about 8 million pounds in metals. I'll show you this to indicate how common asteroid impacts were in the past. I challenge you to identify this structure. It looks vaguely like the moon. That's because it is. It's the south pole of the moon. And because it has no atmosphere, no rain or anything else, it is uneroded. And so our Earth would look like this, except for we have rain and tectonic plates moving and subducting. So our early surface probably looked like this until the oceans came. We do have craters. These are this is a Martian crater. Here's a meteorite on Mars, and hip hip hooray for our little first helicopter that flew on Mars this week. And then here is Mercury that shows lots and lots of meteor impacts. This is sand dunes on the base of this impact. And if we look, we know about craters. There are craters everywhere, even if they're buried, partly buried. This is probably the best example, the Barrington one in Arizona, but they're all over the place. Even some that may not be familiar. The very southern end of Chesapeake Bay was formed by a huge meteor impact. And some of the debris, this is one of my favorite subjects, is that when an asteroid hits or meteorite hits, it will melt the rock and then throw it up in space, and it will fly through space and land some distance away. This is up in Quebec. This is actually now a reservoir, but it's an old meteorite crater. When these asteroids hit, they vaporize, they melt, and they throw ejecta into a blanket, and then this blanket gets buried under rocks. And so you can find this ejecta. These are called tektites, and they're not meteorites. They're what the meteorites cause when they collide with the planet, melt the crust, and then throw this debris in space. And there are clusters of this. Darwin discovered some down in Australia, and sometimes they form as kind of dumbbells in the air, and then they spiral and split apart and form these. Sometimes they just look like odd worry balls, but they also can create crystal. And this is a one of these crystals. This one came from Germany, and it's valued at around $1,600. And you notice how small it is, smaller than an Oreo. But the most beautiful of all tektites are found in Czech Republic near Brno, where Mendel lived. And the impact was over here by Stuttgart, but the downwind flow of this created melted glass. When the atomic bomb was first let off in Alamogordo, it fused the glass as well, and that is called trinitite. But this is moldavite, and a beautiful, beautiful gem it is. Also, a couple that have never been discovered in terms of the crater, but we know that this is diplectic glass that is found in Saudi, and it's called Arabian Glass. And here's a piece in one of the Egyptians as an Egyptian scarab. Plus meteorites are made into ring decorations, and you can see the Widman-Staten lines and knives in particular. I love these. I don't love them, I just hate them, but they're $1 million pistols made out of iron, out of meteorite iron. Most meteorites today are actually found in Antarctica, because every summer, their summer, our winter, scientists go down on snowmobiles and they know where to look. These are glaciers that are moving and they come down slope and they go up, and there'll be lines where the meteorites are drawn up to the surface. And so it's pretty easy to find them. They're carefully sterilized, put in bags. No one handles them with fingers and so on. That's because in 1996, people felt they saw microfossils that may have been life in one of these early meteorites. But it turns out these were forms of calcium carbonate, not life. They look a little bit like bacteria, but they're not. You can also, if you're so inclined, and I do all the time, you can just take a kid's pool, put some plastic in it, and leave it out for a couple weeks. I collect my rainwater and then I filter it, and you will find micrometeorites. And you have to know what you're looking for. They're glassy or metallic, rarely metallic, and they're kind of fun if you're a nerd to have a little collection of micrometeorites. Micrometeorites give many people a cause because sometimes they ruin satellites and even spacesuits and so on. And people love to collect them. This is Robert, who sold his collection. This is his favorite putter, which is made out of a meteorite. And this is a man named Jane. This is his collection, worth about $8.5 million, probably much, much more. The biggest collector that I know is Bill Gates. And you can't even find a picture of his collection, but he has the world's largest collection. To give you an idea, so here is a piece of fall from the Chelyabinsk, only $350,000. And here is a Palacites. Now, you don't have to wait for meteorites. You can go to Japan and buy an artificial display. So this company actually will send up, well, they send up satellites periodically and then they burn up, but they send them up and you can program them to release barium, cesium, strontium, natrium, and all these things. And each of them has different colors. So you can select the color that you want for your own private celebration if you have more money than you know what to do with. So with that, we go to auroras, and something I hope is on your bucket list. And we're at a good time because we're going back into the solar cycle. Our sun, this is the Hertzsprung-Russell diagram, and it's basically an age diagram for suns, stars around our solar system. Our sun started as a kind of blue giant and then went to a white dwarf and then became a medium-sized yellow sun. And it's eventually going to compress, expand. It will expand like crazy, and then it will shrink into a red dwarf. At this point, it will expand to larger than our solar system. But we have about 5 billion years before that happens. But we know our sun is getting hotter and it is expanding slightly. Now, that has a great deal to do because the sun, when it gets hotter and does things we don't know what controls, it erupts with gigantic, what are called corona mass ejections. And these also create a solar wind. And that solar wind races across our atmosphere. People in the past, especially in the Arctic region, where they had red foxes or Arctic foxes, knew it was the fox playing around at night, jumping and creating these lights. Inuits believed it was children or souls of children who would play especially a kind of soccer, and they would kick the head of a dead walrus around, and that would create the light. More recently, it was thought to be the shining armor of Valkyries. But I still like our mythology. This is a sun that is not only middle-aged, it's angry. And this is erupting with all kinds of mass ejecta. They're also associated, these ejecta are associated with sunspots. And the sunspots, they're magnetic, they're created by the eruptions, and they go through cycles. And so here's the sun during a minimum cycle. And here's what we're moving to. The sun is getting more and more spot, getting more and more ejecta. And right now, this is where we are, and this is where we're headed. And all you need to know that this curve is going up. And we had a cycle, a great cycle that lasted quite a long time, from 2012 to 2014. I happened to be doing a lot of Arctic trips, and this was fabulous. And this is worth investing in a trip to Norway or even Skagway. But right now, we're beginning to go in this cycle. And by the way, these cycles repeat on an average of every 11 years. So here it is. And if you look back in time, this is what we're going to. Big cycles in the past. our cycle is predicted not to be really big, but you will see sunspots and you'll see these coronal mass ejections. They're just phenomenal. And when they eject, all of this plasma, electronically charged particles head across space. And this is a scale. There's Earth. And this is how much comes out. It would just completely absorb. Look at these things. When the Earth is active, you will hear of these because they get caught in some cases by, there's a wind produced and they get pulled into Earth by our magnetic sphere. So here's the solar wind heading out, and it's going to come to our magnetic sphere, and it extends in space like a butterfly. It actually is pushed off away from the sun, and all of this geomagnetic solar wind will get caught and pulled in. So here's the solar wind, and it gets caught and wraps around our magnetic sphere, and it comes back. Some of it comes back and some of it comes this way. So you get all of this ionized plasma coming into Earth this way and this way. And when it hits the upper atmosphere, it ignites the gases in the atmosphere, which are primarily oxygen and nitrogen. So those then begin to glow. So this is the strength of the solar wind from the solar flare, comes in both this way, and simultaneously you get at both South and North Pole auroras. So it's cyclic, it gets trapped, and it repeats over and over again as long as there's a very pronounced solar wind. And you will then get these auroras, and this is what it looks like from space. And they can be over the north or over the south. So here is the Aurora Australis taken from a satellite. And they're basically centered on the magnetic South Pole, not the geographic, because that's where these plasma things come in. They come in fairly high, up about 80 miles. And here's a picture showing how sometimes the magnetic lines pull these down and they heat up. So they can heat up oxygen up here, they can heat up nitrogen, oxygen again, and nitrogen again. And each of those elements, depending on where they are and how much and how hot they are by the ionization, will give off different colors. So again, anything from 80 to 200 miles. Recall our Noctilucent Clouds, which are below that, but are influenced by meteoritic dust. And here's the polar stratospheric or nacreous clouds. So they're great to see from space. Here is daylight with a little bit of the air glow, and this is daylight meeting the night, and you can sometimes see aurora during the daylight, but they're best seen at night. This is also air glow. Even other planets, this is of course Saturn, and they have their own because they're big enough to have magnetic fields and dipoles. So here is aurora taken on Saturn. The reason we see this is here is oxygen increasing as it goes up. Here is elemental nitrogen increasing. Here is diatomic nitrogen and diatomic oxygen. So each of these, once they're ignited by the plasma of the solar wind, will glow different colors. So this is what oxygen will look like. There's a yellow and a little bit of a blue. This is what nitrogen looks like, red and blue and even purple. So if it's red, it's probably oxygen way up here. Blue, it's nitrogen. Green, it's oxygen. Pink or purple, it's nitrogen again. So you can tell a little bit of how high they are. So this is going to be about over 100 miles. So if it's purely a red glare up here, then it's probably just oxygen lighting up, and it's just going to be a glare. If it is nitrogen and a little bit of oxygen, you're going to get curtains and draperies, and they're going to move because these magnetic lines move. And if you're getting really purple, this is not triatomic, it's diatomic with three covalent bonds, and it will make it very beautiful purple. And these things shimmer, and they, in my mind, they crackle. I've recorded it, and although most people say you can't hear it, but the dogs hear it, so I hear it too. Again, here are satellites. This is aurora all along the upper atmosphere. Here's daylight happening. And this is air glow again. This yellowish color is from sodium being lit up from the oceans, and atomic oxygen, and that little green sheen from diatomic or monoatomic oxygen. Believe it or not, you can create auroras in a little Plantinella bottle, and you run a charge through it, and a magnetic field forms around your metallic sphere, and you get, depending on what gas you put in there, this is nitrogen. And NASA people are basically kids with very expensive toys, so they have shut off rockets filled with strontium and barium just to see what the motion of the ions and neutrons are in space. Just like clouds, there's notation. If you're seeing a cloud, look at how this dances, and you can get reflections. You can describe it, and there are standards for describing it. There can be curtains, there can be a glow, there can be a crown, a pulse, and so on. This is Fridtjof Nansen, who early on described these and did watercolors, but you can get any combination, and they change constantly. And if you're underneath one of these, they are just mesmerizing. If you're off to the side, yeah, it's very mesmerizing. Sometimes challenging to photograph, but very rewarding because your eyes don't see it this intensity, but your computer chip or your film will, which is one of the fun things about it. And just dancing. So you can see why it was a fox dancing around, or Inuit kids playing soccer. And this is what can happen if it's very low and you're right underneath and looking at it. In other cases, it just passes you. And this is a fisheye view. And you can get really, really high. So you're getting a nitrogen up at the top, you're getting oxygen, a little bit of nitrogen, more nitrogen down here, and you're getting every kind of color imaginable. Pulsing, draping. I love this because this is one of the first auroras seen from the space station, and these guys really have a show for them coming up in a couple of years. But this is from the space station looking at elemental oxygen glowing in the upper atmosphere. But you can see the magnetic lines here, and you can see up here is monatomic oxygen and then diatomic oxygen. And here is probably a little bit of daylight coming into this. Now you can get a forecast. I think I have a more current one. There are a couple places I gave on your handout, and you can then go to these and download, and they'll show you something like this. And they'll show you where the aurora will be. And of course, this is night. And what's the probability of seeing it and how strong is it? So if you look down here, you have a maybe, if you're up here at Greenland or up here in Point Barrow, you only have about a 10 to 20% probability of seeing it. And it's not going to be intense, just because that's where we're at right now. But here it is, I think. Yeah, what is this? Yeah, 416. It's still pretty much the same. It's low intensity. But if you were up here, you would at least see something, or at least have about a 20% chance. In a couple of years, this is going to be orange. And you can go on site and see these. And if you know there's a big solar storm, you know that this is going to hold on and stay in place for some time. And sometimes when there's a big geomagnetic storm, these can come down to Chicago. I've seen them in Santa Cruz, and they've even been seen in Rome at certain times. But you need to watch what the sun's weather is like and what kind of solar activity and geomagnetic warnings there are. This is the ISIS images again. Oops, sun, we got that already, sorry. When these geomagnetic storms come, they will be evaluated and given strength in terms of where they are in the flare coming toward us. So the higher number means they're really going to hit us pretty hard. And so this is an absorption frequency, and it shows that North America is going to get hit really hard. And if you're in this band, you have a 90% probability of seeing really strong auroras, and probably very colorful red and purple auroras. So you need to go get on a plane, go up to Moose Jaw someplace, or go to Iceland, Greenland, go to Norway and take a plane from Oslo all the way up to Svalbard, some of the best viewing. And as I said, you can stay in a motel completely built out of ice. The probability of seeing it is also noted by the KP scale. And this equates to the strength of the storm, the geomagnetic storm. So you're going to see it if you're up here at North Point or here in Iceland. But if you're down here in France, you're going to have a very low probability of seeing it. So you can go online and see these, the predictions. NOAA makes them. There's a European Space Agency that makes these predictions, and all kinds of other that I put on your handout. So these are worthwhile watching and being intense. This is just the scale. So up 6 or above are moderate to strong storms. A 9, these will come down to us, 40 degrees north latitude. So they're still absolutely phenomenal. There are sounds that I've made that correspond with the motion, hissing, popping, cracking. Some people think it's psychological, and that some people think it's actually just your breath breathing or freezing when you're breathing in and out. But I love the north. I love extreme north. I love the darkness and the cold. Now, recently, something else was discovered. People have been seeing these for a long time. They're vertical and they're streamers, and they're not really true auroras. They're called strong thermal emission velocity enhancements, almost like the luminosity events. And these tend to be like columns. and sometimes just straight lines, and they go way, way up. And so these are now designated as steves. And sometimes you can get a kind of inversion of the geomagnetic waves, and the aurora can get trapped in here and oscillate back and forth. And these are called dunes. These are very rare, but they have been seen in many, many places. Now remember Noctilucent clouds, they are formed primarily from meteoritic dust. And one of the interesting things is that these transmit and interfere with all kinds of communication, not just satellites, but also cell phone communications. And they do work to bounce communications off in the upper atmosphere. So ham operators have known for long times on certain nights, they can bounce a radio frequency off these things and send it all the way to the other side of the planet. And this is what a noctilucent sequence of clouds looks like in the North Pole. And that would be very, very important in terms of knocking out and also possibly using radio wave bouncings. So here's the KP scale again, and you can find these in multiple languages. This is from the Canadian. This is our current one from the 10th of April to the 16th of April. Very, very minor. It depends on where you are. So not higher than a 4, but you really want to get up here, a 6 and above. So this is the aurora forecast, and I give you that website. Now, another concern is these geomagnetic storms, which will potentially knock out all kinds of satellites, also damage the solar panels. Micrometeorites can hit these things. You can create plasma bubbles up here. They can knock out GPS stations because GPS is based on a network of satellites that you time the signal so you know exactly where you are. It will interfere with radio waves, scintillate radio signals. It can, it's been measured, but no one really worries too much about radiation in airplanes, and also interfere with radar. So this is what people worry about, geomagnetic storms, but the good side is they also bring really beautiful auroras. Now, there is a government agency called HARPA, High Frequency Active Auroral Research Program, and they actually send waves up into space and try to interfere with or above the ionosphere so they can generate auroras artificially. And they just want to know, how do these magnetic waves work? But when they're doing this, they occasionally can produce some pretty unique auroras. And here is Jupiter. And interestingly, in Jupiter, you can see the shadows of Europa and also Io and Ganymede, the moons of Jupiter. Here's Saturn, and you see the beautiful aurora. You can see it here pulsing. And they're just a beauty to behold, one of the great phenomena in the sky. So realize we're all stardust, we're all meant to glow, and we're all meant to come from stars and return to stars.